So I'm Brandon Gina. I'm a PhD student at UC Berkeley, and I'll be presenting on our challenge paper on low-power wide-area networks. We're really excited about the impact of these LPWANs, the idea that you can just deploy one gateway and cover an entire city, entire campus, all the sensors that you've deployed. However, I'm here today to talk about a problem, a challenge with these low-power wide-area networks for the community to solve. Particularly, we believe that ubiquitous connectivity is not yet met. The needs of it are not yet met by these unlicensed low-power wide-area networks. Particularly, we see significant problems in terms of capacity and coexistence that really need to be addressed, or else applications are going to be lost to newly emerging cellular IoT technologies. So I'm going to, in this presentation, talk about why we came to that conclusion and hopefully let you make a decision for yourselves. So the two classes of networks I'm going to be talking about. First are the unlicensed low-power wide-area networks. These are things like Sigfox, LoRaWAN, Weightless. They're deployed in unlicensed bandwidth. In the United States, this means the 902 to 928 megahertz band. They can be deployed in many ways. You can go to DigiKey right now, buy yourself a LoRaWAN gateway, pop it up, cover this entire hotel with a network. And what's really exciting about these is that they are in that unlicensed band. As a researcher, you can make modifications to these protocols, deploy them in the real world, test them out as much as you see fit. And that's really exciting as a researcher. The second set of protocols that are really impactful in the space are the new cellular IoT protocols. These are things like LTE-M and narrowband IoT that target machine-to-machine communications. They're sort of normal cellular protocols in that they're on the unlicensed, they're on the licensed cellular bands. They're on managed networks. They've now been rolled out through the entire US and worldwide. On the right here, we have a graph showing the range and throughput of many of these different networks. You can see ranges in several kilometers for all of them, and network throughput can sort of span from about 10 kilobit per second to 1,000 kilobit per second. And the reason we're so excited about these networks is that the ubiquitous applications that need them already exist. The ecological sensing applications like ZebraNet and Great Duck Island were really influential at the start of this community. And there are newer emerging applications like city-scale sensing. The idea that you can put air quality meters every block throughout a city and get a fine-grained view of what the air quality is like in your city, in your town. Those are really powerful ideas. And they're only increasing, and as the number of deployed devices increases from billions into trillions, the import of these wireless networks is going to grow even greater. And so the question that we were interested in investigating in this work is, do these LPWANs, do they really meet the ubiquitous connectivity needs of real applications? And there's two parts to this I'll talk about. The first is, how do you determine what is met or not? How do you determine suitability? And here we're going to focus on throughput rather than latency or energy, which are both very important topics for several applications. We're then going to use this metric to explore suitability for a particular application use case. All right. Okay, and so the goal here is that we can compare applications and networks to each other. And the problem is that ubiquitous applications are really wider than even a single wide area gateway's coverage. We're going to need multiple gateways to be able to serve them. And this means we're going to need to account for the physical space of the deployment and the range of each of these gateways. And the simplifying abstraction we're going to make here is that we're going to think about the density of the data transmissions that are occurring. And so we refer to this metric as bit flux. This is the idea of throughput of a network divided by the coverage area of the network. And as with many ideas in life, this was first mentioned by Mark Weiser. This is adopted from one of his ideas from the 90s. So to give you a sense of what this looks like, for an application, what we're going to do is we're going to look at each device, what its uplink requirements are, how much data it's transmitting. And then we'll sum this across all deployed devices and divide between the deployment area. For a network, we'll actually look at a single gateway's good put. and divide that by that single gateway's coverage area. And the number that we get here is a measurement of the density of data that the network is capable of supporting uplink for. No matter how many gateways we deployed, we can make this a wider area thing that's covering an entire region, or we can just have one gateway, but that density is still unchanged. However, there's this idea in especially wide area networks of spatial reuse, that we can reduce the coverage area and deploy additional gateways in order to increase our capacity. And bitflux accounts for this too. So as you reduce coverage area, you're increasing bitflux accordingly. And so if we take a look at a particular network, here's LoRaWAN. So LoRaWAN in the United States has 64 channels to use for uplink. However, it's reduced significantly by its sort of simple Aloha access control mechanism. And so putting these together, we get a measurement of its bitflux at about 2.6 bits per hour per meter squared. And we can measure several of these networks and plot them, and note that they sort of span multiple orders of magnitude in terms of their throughput. However, this idea of range reduction means that each point is not really sufficient for categorizing a network. Actually, each network is defined by a curve where you can reduce range and increase capacity. And so you can pick any point to live on this curve for the capacity of your network if you're willing to deploy additional gateways. So now that we've talked about networks a bit, let's talk about a particular application example. In the paper, we cover about a dozen different applications. If you're interested, you can take a look. Here, we're going to talk about household smart electric metering. In California, PG&E has deployed smart electric meters on basically every house. And each of those meters sends about 250 bytes of data up to the cloud about every 4 hours. This isn't a whole lot of data, but the meters are very densely deployed. And so 400,000 of them or so throughout San Francisco alone. And so going back to that bitflux figure, we can plot this application as a line. And now every network that is above this line on this figure is capable of serving the needs of the application. We see that Sigfox wasn't initially above the line, but can reduce its coverage significantly in order to meet the application needs. And so all 4 of the networks we're demonstrating actually can support the requirements of this electric metering application. However, there's still some problems. And so what I'm going to change to here, this is a plot of that same electric metering application, but in terms of number of gateways throughout San Francisco versus percentage of the network that's being sort of used for this one application. The first thing to observe here is that the cellular networks really have no problem with this. LTM can deploy one gateway and cover electric metering throughout all of San Francisco without 1% of its capacity used. The unlicensed band protocols, however, have a trade-off to make. They can use a significant proportion of their capacity on this one application, or they can deploy very many gateways. And this really illuminates 2 particular problems that we want to point out with the unlicensed LPWANs. The first is this capacity problem. Sigfox in its sort of initial range wasn't able to meet the capacity requirements of the smart metering application. And this is really disappointing because Sigfox's range is actually big enough to cover all of San Francisco with one gateway. But its capacity, its ability to uplink data is not. And so many additional gateways are going to have to be deployed. Solutions for this are relatively straightforward, and our community has already begun the path of solving these issues. Ideas like improving the access control mechanisms are relatively obvious. You can change to TDMA and get about 5x the uplink. Other ideas, you can be like Snow and maybe use the TV white space in order to increase your bandwidth. And that's also going to increase your capacity significantly. I'd note, however, that many of these capacity improvements come at the cost of increased energy usage. The other problem besides capacity is one of coexistence. And this one's really more pernicious. The problem here is that LoRaWAN, in this example, could meet the application needs of our smart metering application, but can only do so by giving 50% of its network capacity to that one application. And remember that I defined capacity for LoRaWAN as using all 64 uplink channels. So what we're really saying here is that we're dedicating 50% of the 902 to 928 megahertz spectrum for electricity metering. And the real problem here is that you can't just dedicate that much spectrum to one single application. You're going to have to share it. Especially in urban areas, there's not going to be one network deployed. There's going to be many that are overlapping in the same space. And so each of these networks is going to have one set that are sharing the same unlicensed band. It's going to have sort of one set of capacity that it's sharing between it. And the solutions for this coexistence problem are also harder. We need methods to be able to negotiate and coordinate between networks. Particularly, a problem is that without buy-in from all the deployed networks, it really doesn't matter what you're doing to increase your capacity. So if you've created the world's best TDMA algorithm for scheduling your LoRaWAN uplinks, the problem is if your neighbor is also deployed and doesn't care about that, their packets will collide with your packets. And now you've got reduced capacity due to this coexistence issue. And one extra point here is that cellular protocols, they don't have this problem. When LTM and narrowband IoT are deployed, they don't have multiple overlapping networks. They really are just one network. And that means that they can make the choice on how to spend capacity. Maybe they don't want to dedicate 50% of their capacity to electric metering, or even 1%. But maybe if the money's there, they do want to do that. And at least they have the choice. They can sort of choose what they want to do. And we see this as a very large problem because new emerging applications are possibly going to end up going to cellular rather than unlicensed band. And this is really disappointing as a researcher because once all the applications leave this unlicensed long-range band, the research becomes less valuable here. And so we're posing this as a challenge to the community. We really believe that solutions in capacity and coexistence are needed for these unlicensed bands so that they can maintain being this hotbed of sort of research that we're interested in them being.